Okay. What do I explain now? So I've explained that type of question. Okay, I think I just start from the beginning. So I basically want to try explaining all of quantum physics, nuclear and quantum physics, to the best of my ability. So the first thing that we start with is I guess actually let's share the stream first. Okay. Okay, the stream's shared now. So the first thing I want to do is talk about the Geiger Marsden Rutherford experiment. So let's start typing this down. So we got the Geiger Marsden Rutherford experiment. So basically what happened during this experiment was they took a bunch of gold foil. So let's get some gold. So they took a bunch of gold foil, right? Let's just pretend that's some gold foil. Yeah, they took a bunch of gold foil. That's gold foil right there. Right? Uh right, so they took a bunch of gold foil there, which is what is gold again? 79 167. So that's AU 167.79. So they took a bunch of that really thin gold foil sheet, so it was like literally like that thin. So what they did there was they took a alpha particle, or struck with. They took a alpha particle gun. So they took a like they took a gun here that fires alpha particles, which are helium atoms. So right, they took alpha particles that fire helium atoms out. And what they did with that was basically they just fired it directly at this gold foil here. So with this, what basically happened is they noticed that when the alpha particle like hit the gold atom, so you have the gold atom here, you'd have like this, let's say this is a alpha particle and then this is the gold atom. What they thought should have happened was it would hit it and then it would bounce off, right? But what actually ended up happening is you took the alpha particle and then you took the big gold atom here. What ended up happening is when it fired, it like went through it. And then they had like a little reflecting thingy over. They had like a reflecting concave dome here, which bounced it back at another angle. And they were not expecting this angle at all. They were not expecting that during the experiment. So what they ended up concluding is that whatever is in the atom is basically just a bunch of empty space. All that, it's a bunch of empty space. Right? So what they concluded was that you could basically take most of this and then put a little dot in the middle, and then that would be the actual only solid part. So all these kind of lines, those would pass straight through. But then when you hit the nucleus now, which is like exact there, it would bounce off in the way that they were expecting it to. So this is the Rutherford gold foil experiment. Alright, so basically what came out of the Geiger Marsden Rutherford gold foil experiment. So basically what came out of this is that it suggested that most of the atom was actually just empty space, which makes sense now you think about it, because all the nucleus and stuff is just really small, but the radius of the atom is so big. So how could that make any sense, right? So on the other hand, now we have, remember this part here when things would go inside, it would like bounce off. Where am I getting ping from? Oh, anyway, when it would bounce off, right? So we have this thing now called radius of closest approach, or distance of closest approach. So when you have a nucleus, let's say that's a nice nucleus right there, and you have a particle here, like an alpha particle, and you fire it directly at that, what would happen is that it would basically go really close and then it would start coming back. So when you zoom in here, this distance, this distance here, or let's put this in a different color, that distance right there, that was a distance you could calculate, right? So that's the distance of closest approach. So taking that, right? We have that now. We know what that is. So the next thing we do is basically with the distance to closest approach, we can calculate it because like you have your EK, or the kinetic energy of the alpha particle you're firing off, right? So you got, remember the alpha particle gun, right? Your alpha particle gun there. It fired off the alpha particles with a certain amount of kinetic energy. And that could be calculated using 1/2 mv square, with m being the mass at rest of a proton, v square being c square from the speed of light, right? Right? So you got the speed of light there. So going back to the distance of closest approach, right? What would end up happening is when you have your particle and then it goes around at exactly this point, you would have the nucleus here. It's not touching this. This is a no touch zone. You basically got a force field, right? So at that point exactly, the kinetic energy would be equal to the electric potential energy of the atom. So basically whatever force is going, to draw like a free body diagram, you have the force going in this direction, and then you have the exact opposite force going in the opposite direction now. So you have an exact replica of the same force. So this one is the EP and this one is the EK, right? So basically, now we can calculate that. So the way you calculate that is just use the 1/2 mv square is equal to kq1 q2 over r. So Q1 being the charge of the atom, which is equal to the proton number. So in gold's case, it's 79, and Q2 equal to the alpha particle, which is 2. And then R is what we're trying to solve for. So then we rearrange this whole thing so that it'll be equal to R. So it becomes KQ1 Q2 over 1/2 mv square. And then that's equal to the distance of closest approach. Yay, we have it now. So next thing, well, what's the next thing to do? Oh, yeah, now we have the distance of closest approach, right? So using that, what you would think that, like, if you had a graph of the distance of closest approach here, and then you had the amount of kinetic energy the alpha particle was shot out with, you would see something like this, right? You'd see this kind of graph. However, what actually ended up happening, or actually not this kind of graph at all, sorry. It should be a little bit more curved than that since it's square. So you should see something like this. Like that's what one would think. However, that is not actually what ends up happening in real life. So Rutherford scattering's predictions predict this to happen. So they'll get infinitesimally close to zero when it comes to the distance of closest approach. However, for some odd reason, when you take this, it follows it up to a certain extent, right? You're seeing the actual proper curve there, but for some reason, after a certain amount of alpha particle energy, it basically just plummets. Like, absolutely no idea. So that basically is the highest level of kinetic energy where the Rutherford scattering model actually applies, right? So someone tested this in 1961. I'm pretty sure it was Eisberg and Porter. Their experiment in 1961 basically tested with lead 208. So that was lead 208. They showed that particles with a greater initial energy than 28 mega electron volts. So that's 28 times 10 power 6 electron volts, which is a lot of power, is the largest energy for which scattering still actually follows that graph, right? So at that point, you just see this break, right? Instead of going down, it should go. You basically see it follow, but instead of getting infinitesimally small, it would get bang. Really weird, right? So this was labeled as the energy like that. That's the super high energy of an alpha particle, right? This is basically the size of the nucleus. This. That literally represents the exact size of the nucleus. Right? So using that, right, we know that the total number of nucleons inside the nucleus is like the protons plus the neutrons, right? So you got the protons and then the neutrons. That's equal to the total, which is A. We call it A. That's the absolute total. So there's a super simple equation that relates the number of nucleons, which is the number of total particles inside, to the volume, right? So you have the volume here, and then that is not an alpha particle, sorry. That's supposed to be inversely proportional to the number, it is directly proportional to the number of nucleons inside it, right? Because you know how volume is equal to 4/3 pi r squared? So you have that equation. So R still follows R, right? This, of course, assuming that a nucleus is like a sphere. Then after that, you can basically get what was it? Oh yeah, sorry. The radius cubed is directly proportional to the number of nucleons as well, right? So using these two equations, we can basically come to the conclusion that the radius here is equal to R naught into a power 1/3, because we're basically just doing a cube root to cancel that, right? So, where was I? Sorry, that's the That's a constant, by the way. R naught is a constant. This is the Fermi radius, which is equal to 1.2 times 10 power 15 meters, or 10 power minus 15 meters. 10 power 15 would be absolutely insane. So that's the radius of an atom now. So what we can do with that is we can get the density of an atom, which is represented with this rho, or the weird looking P. So you got the density of an atom is equal to the mass, right, over the volume. So the mass is equal to A times 1 unit, or one, like, unified atomic mass. We'll get to that in a second. So over the 4/3 pi r cubed, right? And then that's also into A. That simplifies totally, or oh wait, I see what I did there. I messed up something in this equation. So what we can do here is it is 4/3 pi r naught, which is the Fermi radius here, cube A. So these two A's cancel out, basically leaving, and then we simplify this even further. So we have 3u, because we take this, put it in the top. Basic algebra, guys, you got it. 3u over 4 pi r naught cube. Right? Now this is equal to this is the equation for the density of an atom. So something that you might notice, right, is if we try to use this in an equation, we have basically the same thing every time. So let's try it for, I don't know, what atom do we try this for? Or actually, no, you don't even really need any atom, because as you might have noticed, the nucleon number here and here got cancelled out, meaning that all of this too is only made up of constants. 3u is equal to 3 times 1.7 times 10 power minus 27, and 4 pi into r naught, which is 1.2 times 10 power minus 15 cubed. You might notice that all these are constants, right? So this basic like algebra that physicians in the olden days did basically explained how nuclear density is a constant. So that's a really interesting thing, because normally when you try to take like a ball or something, right, you have a ball here. So let's say this is a ball. If you increase the volume of it by like putting more air in it, definitely the density will decrease, because you know how the equation of density is, right? So you take the mass over volume. So the thing with atoms, though, is that if you take an atom and try to increase it in size, you have to both add mass. You have to add mass. And the basic repulsion of all the stuff inside it that's clumped around, and then the electrons that are flying around here as well, if you increase the mass, you also increase the volume proportionately. So that basically results in this and this canceling each other out, meaning that the density will remain constant at all times. It will never change. So using this calculation here, we get a value of 2.4 times 10 power 17. Yep. 10 power 17 kilograms per meter cube. So that's for every meter cube of atom, if you have a meter cube of atoms, just imagine 1 meter cube of atoms, you would have 2.4 times 10 power 17 kilograms. That's an insane number. Just to like put that into perspective, that is, God, what weighs that much? What's the weight of an eight-wheeler? Let's say 32 tons to kilogram. That's 32,000 kilos. So if we take 2.42 or 2.4, sorry, and then times 10 power 17, and then divided it by that. So we could fit in a meter of atoms, we could fit 7.5 times 10 power 12. So let's just write that out in numbers, you know? Let's just get that to be written out in numbers. That is, how much is that? That's 100,000 million billion, so that's, wow, that is 7.5 quadrillion. That is quadrillion eight-wheelers. Like, just think about that. The atoms are mad heavy. They're just also mad small. Like, stuff is really interesting. So this is basically the base concept behind our understanding of what an atom is. Right? So let's move on. What's the next topic? So we know now we understand the Geiger-Marsden Rutherford experiment and how he discovered the nucleus basically. What is the next thing? So I should talk about the emission and absorption spectra. Okay, cool. Let's talk about that. So the emission and absorption spectra are basically like lines. So let's look at pictures. So we have the emission and absorption spectra right here, right? This is a continuous spectrum which is combining the emission and absorption, right? So the emission spectrum basically shows, what's it? Yeah, so emission spectra is produced by atoms that emit photons of light. So a photon is basically just a energy that comes off, which is in light form. So the emission spectra is what happens when an excited atom moves to a lower energy state. So energy states, basically, we have a couple common ones. We have basically infinite energy states, but for my education's concerned, we only go up until like 7. And for this example's concerned, we only need to really go up to 4. So we have energy states which are represented as N. So these are energy, you get it? Physicists are very funny, right? So you get N3, N2, and N1, and then N0, which is the rest. So we have lines here. These are not actually equally spaced out. These are supposed to be N. So we have, let's say N over there, and then let's just draw this properly. So all these are just N. So this one would be the 4. This one would be the 3. This one would be the 2. This one would be the 1. And then this one would be the 0. So you might notice that there's increasing space in between these. And that's because as you go higher and higher, they get like closer and closer together. So you get like a mess of stuff up there once you get into super high energy levels. So this is 4, 3, 2, 1, 0. Right? So basically what happens for an emission spectra is when an atom that gets super excited, so let's say it goes wowee, gets a bunch of energy, gets super excited, now it's in the N4, it goes from N0 to N4, right? It gets super excited, right? So once it gets super excited, and then, you know, what happens with excitement? Excitement fades. So once you get once the excitement fades, it goes back into its ground state. Also, hi anti-mage. Aren't you doing the same thing as me? Like, wasn't this your high school? Didn't you do this? Anyway, so it goes back into the ground state. So during this, a photon is emitted, right? Which is basically just a little bit of light. And then it gets picked up in the emission spectra, which is this one over here. So all of that. So you put it in a hot gas, and it does that. Also, you're doing thermodynamics? Jesus Christ, man. I feel bad for you. That's not okay. You're not okay. Are you sure you're good? Thermodynamics? Thermodynamics is scary, man. Yeah, I can understand you are 100% going to be dying. Anyway, I'm just explaining the entirety of my physics term test concepts because it's on Tuesday, so I'm just like doing a little Feynman technique review, and I just decided, you know what, instead of explaining it to an inanimate object, why not I just explain it on live stream? You're on zeroth law. Okay, zeroth law is... Yeah, zeroth law is pain, man. I can understand. I've done some of it in high school, but nothing to a college level difficulty degree. It sucks. It definitely sucks. I can understand where you're coming from. Anyway, back to energy levels, right? So we have the emission spectra, which is emitted when the energy goes down, right? So when delta E is going down, that's when you get an emission of a photon. So you get your thingy here, and then it bang, photon. Right? Makes sense. Oh my god. So basically what we can do next is use this. We have the energy packet, right? We call it an energy packet, photon. It's just a little it's just a little pack of energy, right? It's just a pack of energy. So you just have a mail of energy right there, right? Erase all that. So that energy of the photon is actually linked to a frequency. This is where we get the formula E equals HF using Planck's constant. Oh my god. Planck's constant. Ooh. I hate Planck and everything he's discovered. The guy's a hoe. Honestly, I don't understand how anyone likes Planck. I don't know how anyone chooses to do anything with Planck. Guy's just an ass. Like a contemporary ass. I can't even begin to comprehend how anyone would possibly want to talk to Planck. Planck's a bitch. I hate Planck. Anyway. Sorry, I got a little bit... Yeah, I'm also a chemistry student, so this is truly a Planck quantum physics moment. Anyway, so the energy is basically equal to the energy difference between the energy levels. So you have the energy of N1, and then you have the energy of N2. Those are supposed to be in reverse order, actually. Energy of N2 first. Actually, no, you can be in any order. You just have to go energy of final minus energy of initial, right? So that's basically the energy there. So Planck's constant, right? What Planck's constant does is it's basically just a converter from... You take frequencies and wavelengths and whatever the fuck else and then you turn that into joules or EV. That's all Planck's constant does. Like, because it's measured in joule seconds. So like, if you have a value that's in, like, let's say you have a value that's in joules, and then you divide it by Planck's constant, you get joule seconds. You basically cancel that out and just get seconds, which is how you want it for frequency, which is how you want it for frequency, because hertz is just seconds, right? But then if you have something that's measured in seconds, like a frequency, then you take your joule seconds, it'll cancel the seconds, and then you get the energy based on the frequency. Very cool converter. Right? Fuck you, Planck. So basically what you can do with this equation of E equals HF, in our use case of calculating emission spectras and whatnot, what we want is not F, because F is stupid and we can't do anything with F by itself. We want H, V over lambda, because you know how F is equal to, what's it, V lambda? Because, you know, frequency. That one's meters per second, and that one's, meters per second, and this one's meter. Yep. Yep. Anyway, so, wait, is that even right? I'm pretty sure this is right. Because F over V equals lambda. Yeah, so that's meter square per second. Okay, yep. Okay. I am no longer confused. I'm having so much fun right now. So we have the HC over lambda, right? So then we can erase the V, because we know what V is. It's just C, since everything we're dealing with is light. All light. All of this is light, right? So everything's traveling at the speed of light, right? So basically, I'll just take like a photo from my book and try to explain it here. So this is how the spectras are formed, right? Let's put that there. So for the emission spectrum, we have the the de-excitement of a photon, like of an atom, which emits the photon, which gets picked up here, right? So you put this in a hot, low-pressure gas, and then it gets like not excited anymore, and then from that, we put it through a prism, and then our eyes can see it, right? You can follow along. It's not very hard. So then, for the absorption spectra, on the other hand, it's basically when a cool gas. So like we take a cool gas. Yeah, we take a cool gas, right? Very, very not cringe. Very not cringe quantum physics moment. We take a cool gas, right? And then we have it absorb a photon. So we take the cool gas and then we basically, it like sucks into it. So it like goes in. So we take a photon, which is, remember what a photon is. It's our little energy mail. Yep. Photons are energy mail. That's a great way to put it. I should really use that more. We have a package of energy. That's a photon right there. Anyway, so basically what happens now is that the atom that absorbs it, so we have the cold gas. Let's say we have a hydrogen atom that's at like, I don't know, not zero. Let's say that's at like 3 Kelvin. That's really cold, right? So by adding energy, you know the concept how you add more energy, the temperature goes up? So you just have the same thing. That's the same concept we're going to apply here. So we have this hydrogen gas, right? So we add more energy. Therefore, the hydrogen gas is now at a higher energy state. So going back to that end diagram, we can basically draw like this. So we have the 4, 3, 2, 1, and 0. So let's say it absorbs, goes up to this, right? So what happens there now is, what was it? This becomes unstable. Because when it's at the ground state, very stable. Always. Always very stable. Hydrogen, very stable when it's at the ground state, right? However, if it gets excited, just like your 6-year-old cousin, it immediately starts getting unstable. So you can't trust the gas to be stable up here anymore. So because of that, the photon now has the original absorbed frequency. But after it becomes unstable, like it gets de-excited again. Okay, how do I like rephrase this? You know what I mean? Wait a minute. So absorption. Okay, let's go back to the base of it. So absorption happens when an atom in a cold gas, or of a cooler gas, absorbs a photon of an energy identical to the difference between two of its energy levels. So it absorbs a photon exactly the energy to get it from N1 to N2. So this right here is the photon making up the difference. It's from N2, N1. So that's the photon. That's giving it that little energy boost, right? So that basically puts an electron, right? And it moves it up to the second energy group, to the higher of the energy state, right? So the cooler gas tries to remove the photon now to maintain its stable equilibrium. So you have the photon, right? So now that the absorbing atom is in the higher energy state, right, it is unstable, right, because it's excited. So it wants to emit the photon again to try and get back to being stable. However, the photon is emitted in a random direction. Correct? So this is in a random direction. So that changes the frequency. Because if it's random... Oh, wait, what happened to my hosting? What do you mean? Hello, Maxi MC. Sorry, I wasn't reading chat. I was a little locked in. But my hosting's still here. Still around. Just had a website redesign. I redesigned this website. It's really cool. I put a lot of effort into it, and like I like it. I like it a lot. Especially this entire page and panel. Can you get a free server? I don't know you that well, man. I can't lie. We have all the plans. Show less plans. Bam, bam, bam. Yo, if you want to pay using Gcash, open a ticket. Ooh, yeah, baby. Can we partner? Sure. What server do you got? DM me. Send me a DM. I will probably take a look after stream. You have 400 subs and 94 members. Okay. Yeah, I'm just saying right now, you can hop over to... You see... Come onto the website, right? Go here. Go to billing. I blocked you? Oh, yeah, okay. Makes sense. Anyway, what you want to do here is you want to go into billing. You want to sign up for an account. You want to go to your profile here, right? Go into your billing profile. Let me just... Yeah, let's just do this. I am not unblocking you, unfortunately. So what you want to do here is you go to your affiliate tab here, right? Then you can sign up for an affiliate code. So for example, so I have my affiliate code set to be Ashank. Then you can send this to people, right? So now, let's say I'm on the reference with Ashank, right? I have that. I buy a server. Let's say I have a balance of $14. What can I buy with $14? Let's buy a server for $14 real quick in Queensland, Singapore for... Actually, I'll just do an NA for 2 gigs, 25 gigs of storage. Sure. That'll cost me $3 here. I'll pay through credits. Agree. And oh my god, wow. Okay, I have a server now, and also, I just earned $3 here, but since I bought it myself, it's not displaying. Yeah. Anyway, let me just delete that real quick. What do you mean? What happened to my server? Everything's still there. You're just not in it. I don't know what you don't understand here. Everything is still there. You're just not there. You're not with it. You know what I mean? Anyway, let us go back to explaining physics. Right? So, in the absorption spectra, when the photon makes up that difference, it gets excited, then comes back down. So basically when this happens, right? You remember the emission spectra. So in the emission spectra, this is fired out in the exact same way. So you get that. That's the emission spectra. But in the absorption spectra, it's emitted in a random direction. So you don't know exactly which direction it goes to. That reduces the intensity of the photon, which in turn reduces the frequency. So the frequency goes down. That also means the intensity went down. Right? So now the black lines that you see here in the absorption spectra, I don't know if you noticed, but are exactly, and I mean exactly, where the emission lines are. So meaning that they're 2 parts of the same whole. Wow. Right? Okay, so what's next? What do I do next now? How they provide evidence for discrete atomic energy levels. Right. So that I've explained how emission and absorption work now, actually, but I haven't explained how they link to energy levels. So basically, we have the energy levels or shells. So we have the nucleus, then we have 1 ring of electrons, 2nd ring of electrons, 3rd ring of electrons. So that's n equals 1, n equals 2, n equals 3, and so on. So that can be represented in the graph that we saw before, with the radius decreasing in between. So that's a greater distance there. So that's 3, 2, 1. Speed run through this real quick because we've already been through this. So for the absorption spectra, the evidence for that is basically when you have a white light. Let's just say this is white light. It contains all wavelengths, right? It passes through some gas. That's gas, right? Some wavelengths are absorbed inside this. So let's say green and yellow are absorbed by this. So let's say. So the wavelengths that correspond to this exact energy to move an electron to a lower to a higher one, right? So these wavelengths that, or let's say the amount of energy that like is needed to move it from a 1 to a 2 over here is exactly the amount of energy in the wavelength or the frequency of, let's say, the color yellow, right? So we have that. So every single frequency gets a color. So if the frequency is basically equal to inside whatever is absorbed here, that exact like difference between these two, then that means that it'll get absorbed within here and it won't pass through the other side. Which is why you see, if you shine a white light on a black surface, you see a bunch of the light get absorbed. That's basically the real world thing. So the way that we quantize this basically, or like turn this into there, turn this into that, is we go back into the E equals HF. So we take this, which is the SI unit of frequency. What is the SI unit of frequency? It's in hertz. So what is the SI unit of hertz actually? That's cycle per second, I'm pretty sure. Yeah, cycle per second. So the energy is equal to basically the joule second. This is the converter function into the cycle per second. And I don't know if you notice here, but minus S and S cancel, leaving just the joules. Fun stuff. Great conversions. All right. What is next on the list? Photons are emitted and absorbed during atomic transitions. Yup. Frequency is the difference. E equals HF. Yup. Emission and absorption spectra provide information on the chemical composition. Let's see. How does it do that, actually? Wait. I'm not entirely sure myself. How does it inform chemical composition? Pretty sure it's because of like something, maybe? I don't know. I'll figure it out later. So let's see what else is there to talk about. Let's reset the canvas. Okay, so now let's talk about the relationship between the radius and the nucleon number. Actually, no, we already did that. Deviations from Rutherford scattering at high energies, we did that. The distance to closest approach, we did that. Discrete energy levels, we have not done that yet. Okay, so we have... Okay, basically, let's explain this from the beginning. The Bohr model, there's this guy named Niels Bohr. Basically, what he said is that, like, you have the Bohr model is basically the model of an atom that says that you have a nucleus here with the protons and neutrons, and then you have a bunch of rings around it, right, with all your electrons and whatnot. Make sense? Right. So then... what's it? Yeah. Using that, there is the energy levels once again. So we have the 0, 1, 2, 3, 4. And basically the Bohr model was able to calculate exactly the energy in joules or in electron volts, depending on what you do, of each of these energy levels. So his equation that he came up with was 13.6 over n square electron volt. So how did he get here actually? Let's think about this. So we know that in Bohr's model, electrons had to move in a circle orbit and only in a circle orbit. The second thing is that the energy levels must be only here, 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 or here. These are atomic. You cannot have anything in between, right? We know that. So we have the angular momentum L is equal to n, which is the energy level h over 2 pi, right? So n, where n is equal to 1, 2, 3, 4, etc. So the total energy in this case would be the kinetic energy and the potential energy, right? So that's the kinetic energy, and let's just call the potential energy U. So that's a 1/2 mv square plus U, which is the potential energy is what? What is it equal to? The attraction. Yeah, because the kinetic energy is the force with which it swings around, but then the potential energy is that basically. So we have to use the k q1 q2 over r, which is the electrostatic force. So, but then q1 q2 are the same, which is just the elementary charge. So it's just e square over r, and then that's also negative because it's potential, not enacted. Okay, so far all this is making sense, right? So how do you do this? We do the I think that now we have to equate the kinetic energy to something. So it's a circular orbit, and kinetic energy related to potential energy. So that means it has to be an inverse square law, because basically d over r square, or for every distance that you go away from your target object, you have, this is the radius. This line here is the radius. This one. So r square. So basically 1 over r square. That's inverse square law. So the further you get away, the force decreases by 1 over the square of the radius, not just the radius. So basically it says that, like, if you're super close, like there, it's going to be a strong force. You got a really big force, right? But then if you're over here, you get like a medium force. And if you're like all the way out there, it's like absolutely nothing. Okay, so that means that this has to be negative 1/2 u. Since, yeah. So substituting this into the equation now, we got E equals, we have everything in terms of U now. So that's negative 1/2 U plus U equals 1/2 U. Right, so since it's 1/2 U now, we get... We have to multiply this by 1/2. So that turns into E equals negative KE square over 2R. So then... What now? We have the equation for energy. What's next? I have to link it to the angular momentum next because I have to do something with this R because all the rest of these are constants. R is the only thing we don't know. So we have to somehow get R in terms of N. So you have to get like N of R. Yeah. So next thing we do is L equals NH over 2 pi. What's next? So angular momentum is also equal to the mass. So we're using the mass of an electron into the velocity into the radius is equal to NH over 2 pi. And then we isolate for V. So that becomes V equals NH over 2 pi over MER. So that goes to the top. That's equal to NH MER over 2 pi. Right? Now we have the velocity. So using the velocity, we go back into which equation? This one. Go back into this equation here. So since that's what is that? KE square over two R. So that's minus KE square over 2R. What do you do here? Coulomb force for centripetal force is now what? I have to somehow relate these two. What do I use here? Coulomb force. So that's equal to KE square over R square is equal to. We take the MEV square over R. So now we have V. So then we just put it in. I think I should really simplify this. This is ugly. So let's just make that NH bar. Because H over 2 pi H bar. So NH bar over MER. That works. Alright. Then we sub it into the equation. So that into that V. So KE square over R square equals ME NH bar over MER square. So this ME and that ME will definitely cancel. Right? Or hold up. If I substitute that there, it'll be there, and then it'll be that. No, it won't cancel because M E over R, and then that one is now NH bar M E R square, and then I think that's it. Yeah, so it's N square H bar square over M E R cube. Then we solve for R. Oh, that's still equal to KE square over R square. So now we have to like cross multiply this out, so KE square MER cubed equals R square N square H bar square. So this and this cancel, ME. So then yeah, so it just becomes R there. So that leaves us with R equals N square H bar square over KE square ME. Bang. Okay. So we put this R, now that we have this R, we go all the way back into this energy equation here. Alright. Now we have R. So we have E equals KE square, or minus KE square, sorry, over 2 times KE square ME over N square H bar square. That will be equal to K square E power 4, right? ME, only one of those. And then that and that. That will be 2H square N square. That's looking a bit more recognizable now. So then I want it to be in 1 over N square, so we just erase this N square and then multiply it out. Right? Because that's how you get the over N square. So then all of this is constant. So in theory, this should go to negative 13.6 times 1 over N square. Then that'll be negative 13.6 over N square. EV. Yep. Whew, that was a long one. Okay. That's like it's a long ass derivation. I don't think I'm ever gonna have to use that if I'm being for real. Okay, so then oh yeah, back to the angular momentum, right? So we have L equals mv r. It's from that derivation actually. So we have mv r equals nh over 2 pi. So basically what happens here is that the angular momentum, it can only go up or down by like set increments, right? So because of this entire derivation we got here, it's minus 13.6 over n square EV. So using angular momentum, you can get the energy, and the energy will always have this. That's the constant of proportionality. Woo! And n always has to be. So n must always be part of all real positive integers. Very cool. So that explains that. Okay, it's been like 20 minutes? No, it's been an hour. Okay. All right. God damn. What are people up to? What's going on here? What's up? Okay, so that's the entirety of what's it? What we know about the structure of atoms and the relations with energy and all that, right? So, oh yeah, just something to note that like for the scattering experiments, so for the Geiger-Marsden Rutherford experiment, the reason why we only consider the repulsion to be EK at the turning point, right? So when we have that, and then we have the turning point right there, the reason why we can consider EK to be just the electrostatic, or wait, electric, electrostatic force, yeah. The reason why we can assume this is because it's small as shit. So like, not that small. So no other force really matters at that point. No other force can really impact it aside from atomic forces, which is the only thing we deal with here. Oh, that was a long ride. Alright, let's see what people are up to. 6 people on? Damn. They're playing duels? Damn. Okay. Oh my god. What is the next thing? You know what? I'm gonna end stream. I'm gonna do the rest tomorrow. After I get back from school, I'm gonna like review the rest. Because my exam for physics is directly tomorrow. Or at least maybe I'll do it a little bit later and take a break. I'm sitting here for an hour.